So now that we understand where all of the equations come from for calculating the forces in the cables, I'm going to walk through an example of how to do these calculations so that you have something to check against before you get into the problem. So either feel free to follow along with me or go ahead and just pause the video right now on this example and take a go at doing these calculations yourself. And then feel free to skip to towards the end where I'll be showing the values that I calculated to see if we're getting the same thing. So for this example, I've just taken a scenario here that we have a bridge that's 72 meters, has a height difference, highlighted here just so we get some visuals, a span of 72 meters, a delta H of 3 meters, as well as I've given us some geometry to explain, to show where the anchors are. So on the high side, I'm giving you that the alpha is 23 degrees, and on the low side, that the alpha is 19 degrees. Now I want us to do this cable analysis considering the loading case of dead load plus live load, which corresponds to live load sag, right? And why I chose part of this geometry is this is the same loading case that we had when we calculated the loads for a 72-meter bridge, and that came out to be 4.33 kilonewtons. So our distributed live load, 4.33 kilonewtons per meter. I missed a unit here, right? There should be kilonewtons per meter there. So the aim of this example is to calculate the maximum force in the cable so that we can design our cables, in addition to calculating the tower reactions. These are the two outputs of this analysis that we need for design. So walking through this, start with the main span cable forces. And I apologize if this is going to seem a little bit slow and dry, but I'm going to walk through and write out all the steps. So if you want to keep the video going on in the background while you calculate yourself, great. Otherwise, feel free to skip forward. I'll put time marks, or you'll have some time marks to know where different aspects are if you want to check your answers. Okay. So as I said before, we're in the live load case, so we need to be operating with live load sag. So HLL, if you remember, this is equal to 6.1% of the span, right? So it's just 6.1% times 72 meters. If you punch that into your calculator, you should get 4.392 meters. Great. We can now use this to calculate our horizontal tension. So P sub H is equal to WLL times L squared over 8HLL, right? We calculate, if we plug in our numbers now, WLL we had before is 4.33 kilonewtons per meter. Our span was 72 meters, all over 8 times 4.392 meters. And if you see all the units, we have meters. We forgot to square that, right? We have meters squared over meters. They all cancel, and we're just left with kilonewtons, so we know that our units are correct. And if you run that, you should get 638.85 kilonewtons. All right, so now with P sub H, we can start to calculate. So remember, we're in the main span cable forces here. And after pH, we need to understand the geometry of our main span. We want to know what our theta values are, right? So I'm just going to scroll back up quickly to revisit this, right? We just did P sub H. Now we want to get into theta high and theta low. All right. So theta high, we calculate as the inverse tangent, or arctan, 4 times HLL plus delta H over L. And theta low is the arctangent of 4 times, oh, not dead load, HLL minus delta H all over the span. We plug in the numbers, right? We just calculated this, right? It's 4.392 plus delta H, I said it was 3 meters. That's all over 72 meters. And this all now, if we run this through calculus, you see all the meters cancel, which is good. Get 15.94 degrees. Make sure your calculator's in the right units. All right, this one's a very similar one, 4.392 minus 3 meters in there, all over 72 meters. And what would you expect this to be? We expect it to be a little bit less, right? Because we're subtracting, and that's the way the tangent function works. And we get 11.44 degrees. All right, so with our theta values and our pH, right, let's just draw a quick little schematic. This was our theta, this was our pH. Now we can start to calculate PV and then get to PT, right? So PV, and let's know which side we're on. Pi, you go back up and find that equation, pH times the tangent of theta pi. So 638.85, tangent of 15.94. And if you run that, you get 182.50 kilonewtons. Make sure you're getting your units on all your numbers here. Okay, similarly, PV low, right? It's just pH tangent of theta low equal to 638.85, tangent of 11.44. Run that, you get 129.26 kilonewtons. All right, now we can calculate PT high and PT low. So PT high is equal to pH over cosine of theta high, and that is 638.85 over cosine of theta high was 15.94. You run that and you get 664.41 kilonewtons. Very similar equation for PT low, right? pH over cosine of theta low. So 638.85 over cosine of 11.44. Just double check, 11.44. You run that, and you get 651.80 kilonewtons. So let's notice something now. As we've been calculating these forces, what do we notice is the difference between the high side and the low side? We see that on the high side, our forces are a bit larger than on the low side, right? We have 182 kilonewtons versus 129 for the vertical component. And then the total force, they're closer together because the horizontal component really dominates. Yet we still see that difference. So it's just something to note that on the high side of your bridge, you have higher forces, for at least the geometry that I'm describing here. And that's pretty typical for the main span. So it's a good just gut check to have. By going through this example and seeing that, when you're calculating the forces on your own bridge and doing that design, you should see something similar. And you should know if you've made a mistake, if you have something else. So it's just sort of calibrating your gut and your engineering judgment to think about that. And we all understand why that happens based on the nature of the cosine and sine functions, as well as the exercise we went through and looking at that free body diagram of just a little segment of cable. Okay, so we calculated all of our main span forces. Now let's go ahead and calculate our back stay forces. So instead of just laboring and plugging and chugging, I'm just going to go ahead and show you the numbers and pause it. If you don't want to look at the answers right now, you can pause it right now and look at the alpha for the low, alpha for the high, as well as all the equations here. Run those equations, and what you should get is something like this. So I've differentiated this for the low and the high side and calculated the tension, the vertical component, as well as the reaction of the tower. So let's look at the low side real quick. As a gut check, we should know that the horizontal component's dominating, and it's equal on either side. Yet, let's compare the theta values to the alpha values and see how that's changing our geometry. As we go from, so let's go back up to this figure here. As we go to a steeper angle, a steeper alpha from theta, we should see the magnitude of the tension, PT back, increase, right? So on the low side right now, we calculated theta low to be 11.44. See that here? 11.44. Alpha is now 19. So we're increasing that cable angle. So what should we expect to see between PT main and PT back? We should see PT back be higher, which in fact we do. We go from 652 to 676 kilonewtons. So that's a good gut check of, hey, we probably did that right. Similarly, we should see a difference in the magnitude of the vertical components. That's what's leading, because the horizontal components are the same, the vertical component should be inducing that change. And we see that. We see 129.3 versus 220. And that's all based on the angle. So you see how the change in the angle of the cable, that geometry change, really increased the vertical component of the tension force. I'll leave it to you to check that on the high side, but you see that we have an even steeper angle now. We went from a theta high of 15.94 all the way up to 23. So much larger increase than on the low side, and you should see the magnitude of change increase there as well. The last thing I want to draw our attention to is the reaction at the tower. So we see on the low side a reaction of 349 versus on the high side of 465. Seeing that we have a much higher reaction on our high side tower. So it's just in line with what we've been talking about the high side with that steeper angle having more force in it. And that's why we have a limit on delta H. So if we didn't have a limit on delta H, we'd come up with very different forces in our cables because we have really steep angles. So that's why we limit delta H. Remember what that is, right? Delta H has to be less than or equal to L over 25. And that's to just maintain control over our forces in our cables in addition to the steepness of the bridge. Those are two reasons why we have that relationship, or that design check there. So now let's sum up what the maximum, or let's not sum up, let's identify what the maximum force in our bridge is and finish this question. So the maximum force, we look through all of it, it is equal to PT back on the high side, right? And it's equal to 721.8 kilonewtons. So you see that right there. And then the maximum tower reaction is equal to the high side, right? And that's equal to 464.5 kilonewtons. So let's give some food for thought. Can you imagine a case where your low side tower reaction might be higher than your high side tower reaction? What geometric constraint could you change in order to get that to happen? Take a moment to think about that. So if you were thinking alpha, you're right. If we really lowered alpha, say we dropped our anchor and we just made a super steep anchor right here, that would really change what this tower reaction is. And that might, depending upon all the geometry and the numbers, you might be able to get, if you had a super steep alpha, you might be able to get to the point where your low side tower reaction is actually higher than your high side. Typically, we wouldn't want to design something like this, but I just want you to go through that process of thinking about what can be changed. Okay, so let's go back. So back to the problem statement. Based on, we're just going through an example of calculating all the forces in our cables, but we just calculated the maximum force in the cable as well as the tower reaction, and we're good to go. So hopefully you were able to follow along and check your own calculations, plug in your own numbers for this. And next we'll go into actually using the results of this analysis to design the cables, and then we'll go ahead and use the resultant force for that vertical reaction in a future analysis on the abutment.